When we talk about artificial intelligence, popular media often uses the imagery of glowing digital brains and pulsing synapses. But stripping away the biological metaphor reveals a colder reality. Neural networks operate entirely on unthinking mathematical computation, built on a rigid grid of equations. To understand how this works, we have to isolate the smallest unit in the network, the node. Rather than acting like a biological cell, a node is strictly a basic computing unit. It receives numeric inputs, runs a calculation, and passes a single numeric output down the line. Every node runs this exact equation. It takes an input, x, and applies a weight, w. Multiplying them dictates how strongly the input influences the answer. The b is the bias. It's an extra number added to the sum, shifting the result up or down independently. Strip away the science fiction terminology, and a single AI node is nothing more than a linear equation designed to calculate influence. But there is an immediate flaw with that basic equation. It creates perfectly straight, linear lines. The data AI needs to process, like speech patterns, image pixels, and human behavior, is messy, heavily curved, and deeply complex. Straight lines cannot map a curved reality. This graph shows the mathematical solution to that limitation, known as an activation function. Here, we are looking at a common one called ReLU. The function creates a straight line that bends sharply at 0, discarding negative values. By passing our node's weighted sum through this activation function, we force the output to bend. This introduces nonlinearity. Connecting thousands of these bent lines together allows the network to suddenly wrap its calculations around highly irregular data points. The activation function bridges the gap. It is the mathematical upgrade that takes a simple straight-line calculator and turns it into a system capable of mapping the messy physical world. A single node mapping a single bend is incredibly weak on its own. To process heavy data, we have to group these nodes into layers, connecting every single node in one layer to every single node in the next, creating a dense web of calculations. This animated diagram illustrates how we scale the math up. Instead of calculating one node at a time, we use a layer-wide matrix equation. The network takes a block of input data and multiplies it against a massive grid of weights, crushing hundreds of node equations simultaneously. We call this continuous cascade of math the forward pass. The data pushes from layer 1 through the hidden layers, calculating nonlinear equations until it hits the final layer. The result is a single output prediction, which we call y-hat. Stacking these layers acts as a unified prediction engine. You can feed a completely random array of pixels into the front, run the matrix math, and push out a definitive guess at the other end. There is a catch. Because a fresh network initializes with entirely randomized weights, its very first prediction is guaranteed to be completely, spectacularly wrong. To fix this, we apply a brutal reality check called the loss function. This equation displays the mean squared error. It mathematically isolates the difference between what the network guessed, y-hat, and what the true target answer actually is, y. That difference generates a raw error score, represented by L for loss. The neural network now has a singular, organizing goal. It exists entirely to drive this loss number as close to 0 as possible. The initial failure is entirely by design. By generating a prediction, checking the true answer, and mathematically defining exactly how wrong it is, the AI establishes the prerequisite it needs to actually learn. Generating a massive error score at the end of a forward pass leaves a practical problem. The network knows it made a mistake, but it has to figure out exactly which of its millions of individual weights caused the failure. This is where backpropagation comes in. Using the chain rule of calculus, the network takes that final error score and works backward. It traces the math through the final layer, then the middle layers, all the way back to the start. Here we see the gradient notations for weights and biases attached to individual nodes. These gradients act as mathematical arrows. The chain rule works backward, assigning a specific numerical value to every connection, representing exactly how much that weight contributed to the error. Calculus provides the network with a microscopic, perfectly accurate map of its own mistakes. There is no human intervention required to assign blame, The derivatives locate the exact source of the error automatically. This diagram displays gradient descent. The network subtracts the gradient from the current weight, nudging the number opposite the mistake. Eta is the learning rate, acting as a control valve to limit the corrective step size so the system doesn't wildly overcorrect. This single formula brings the entire macro process into focus. This is a massive optimization problem. The network runs the forward pass, calculates the loss, backpropagates the blame, and updates the weights. Then it repeats that exact cycle over millions of batches and epochs. The final result of all this math is a system that can accurately identify a stop sign or generate a paragraph of text. Neural networks do not possess intellect or thought. They are simply relentless loops of guessing, failing, assigning blame, and nudging numbers until their output perfectly mirrors reality.